Electromagnetic radiation. Electromagnetic radiation covers a wide spectrum of wavelengths and frequencies. Light occupies a very small sliver of that spectrum, right over here. And then it's blown up here, so you can see, right, indigo, violet, blue, green, yellow, orange, red. And down here, gamma rays, X-rays, ultraviolet, infrared. So you can see what a tiny piece of it is the visible light. Microwave, FM radio waves, AM, and long radio waves. So you have increasing frequency or energy going from right to left. Electromagnetic radiation is carried by photons, which are packets of electromagnetic radiation which demonstrate wave-particle duality. Wave-particle duality is where EM radiation and matter, okay, so this would be like light and electrons, can each be explained as particles or waves depending on the experiment or phenomenon. It is a key aspect of quantum mechanics. The results of quantum mechanics, including photons, are used in much that will follow in this course. Understanding quantum mechanics is beyond the scope of the course, but can be explored in these courses: Algebra-Based Physics, AP Physics 2, and Chemistry Honors. All electromagnetic radiation travels at the same speed through a vacuum. That includes light, X-rays, infrared, all the same. That speed is called the speed of light and has the symbol c. c is 3.00 times 10 to the 8th meters per second. There is an inverse relationship between the wavelength and the frequency of any wave such that their product equals the speed of light. That's pretty cool. So in the case of EM radiation, the wave speed is c, so c is equal to lambda nu. C is the speed of light, lambda is the wavelength, and nu is the frequency. The wavelengths of some electromagnetic radiation, including light, are very small, so are sometimes given in nanometers, nm. 1 nanometer equals 10 to the minus 19th meters. Nano kind of sounds like 9, doesn't it? When wavelengths are given in nanometers, remember to convert them to meters for calculations of frequency or energy. The frequency nu is measured in oscillations per second, and the unit will be seconds inverse, right? That's oscillations per second, or hertz, Hz. Each photon has energy given by E is equal to h nu. E is the energy of the photon, h is Planck's constant, and nu is the frequency. Planck's constant has a value of 6.626 times 10 to the minus 34th joule seconds, or 4.136 times 10 to the minus 15th electron volt seconds. Well, what's an electron volt? It's a unit of energy, and 1 electron volt is 1.6 times 10 to the minus 19th joules. E equals h nu can be rewritten in terms of wavelength, or lambda, to make it more convenient for cases in which the wavelength is provided. So we solve c equals lambda nu for nu, and we get nu is equal to c over lambda. So what's nu? C over lambda. Substitute that in for nu, and we get the energy of a photon is hc over lambda. And once again, E is the energy of the photon, h is Planck's constant, and nu is the frequency. Energy for individual photons is usually given in electron volts. The energy of large number of photons is often given in kilojoules per mole, which is written as such. 1 kilojoule equals 1 times 10 to the 3rd joules, or 1,000 joules. We have Avogadro's number here, 6.602 times 10 to the 23rd particles per mole, or mole and -1. Since each photon will be emitted or absorbed by one atom or molecule, a mole of atoms or molecules will absorb or emit the energy of a mole of photons. Mole is very convenient in chemistry, isn't it? This chart shows the relationship between the wavelength and the color of light and the energy of 1 photon of that light. So we have our wavelength, lambda, in nanometers on the top, 400, 500, 600, 700. And then right below it shows the photon energy in electron volts, where of course 1 electron volt is 1.6 times 10 to the minus 19th joules. Let's work a problem. Visible red light has a wavelength of 650 nanometers. What is its frequency? What is its energy? Give the problem a try, and when you're done, go on to the next slide. We list our givens. We have 650 nanometers, the wavelength, and then we have the speed of light. That wasn't given in the problem, but this is one of those constants you should probably memorize. We want to find the frequency and the energy. So we have our first equation, speed is lambda nu. We solve that for nu, and we get nu c over lambda. Here's our speed of light. Here's our wavelength, but what do we have to do? Convert that to meters, because the speed of light is in meters. So we have 10 to the minus 9 meters is 1 nanometer, and we get a frequency of 4.6 times 10 to the 14th hertz. Now, what's the energy of this red light photon? Okay, we have our givens again. This time we use A is equal to hc over lambda, which of course is also written as h nu, but this time we have the wavelength. So we put in Planck's constant, speed of light. Here's the wavelength, which we convert from nanometers to meters, and we get an answer of 3.06 times 10 to the minus 19th joules.